Before start the seminar, I would like to give a brief introduction. Dr. Waals. Dr. Waals is now assistant professor in Department of Material Science and Engineering, and he's an expert in two-dimensional materials, definitely including materials, physics, and devices. And Dr. Waals received his master's degree in physics from University of Manchester in 2012. Okay, in 2016, he earned his PhD degree from University of Manchester for his work on interfacial interactions between graphene and hexagonal boron nitride. During that time, his principal contribution was to understand the complex commensurate phase between graphene and hexagonal boron nitride. Upon completion of his PhD, Dr. Waals was awarded the Engineer of Physical Science Doctoral Prize Fellowship to continue his research. This resulted in the observation of microscopic dynamic behavior in 2D interface and a novel sequence of composite supermolar structure. In 2018, Dr. Waals was awarded the British Council's UK Israel collaborative grants, and then he worked in the Tel Aviv University in the femtosecond nano laboratory to work on the femtosecond optical phenomena in 2D materials. Dr. Waals' current interests are in string engineering and the emergent phenomena in 2D crystals. Welcome, Dr. Waals, to give us this presentation. Okay, now it's your time.
Okay, thank you for the very kind introduction. I'll just mention that I joined NUS in November, and I've had a very warm welcome since I arrived. So I'm very pleased to welcome you all this morning and to introduce some of our more recent work. Okay, so today I'm going to talk about piezoelectricity and ferroelectricity and hexagonal boron nitride. It's worth mentioning straight at the beginning that these two properties are not expected to be seen in hexagonal boron nitride at all. So piezoelectricity requires some piezoelectric polarization, which we don't expect to see for hexagonal boron nitride. And ferroelectricity relies upon spontaneous polarization, which does not exist in regular hexagonal boron nitride. So today I'm going to hopefully show you some of the little tricks we've done to try and eke out these properties for the different systems. Okay, here we go. So I split the talk into three. I wanted to introduce to you the topics of van der Waals crystals and van der Waals heterostructures, for which hexagonal boron nitride is one, and really to give you the perspective of hexagonal boron nitride within that. So where does it fit into the current research, and what are we using it for, and why is it useful for that? And just to give you some perspective so that you understand that when we have this piezoelectricity and this ferroelectricity later on, how it's going to be useful and where it's going to go into our samples. Okay, so let's start with the introduction here. So I probably don't have to introduce graphene too much. It's the first of the van der Waals crystals to be exfoliated down to a single atomic layer in 2004. But it's really the first in a large set now of 2D materials. So we have graphene, transition metal dicalconides, hexagonal boron nitride, which we'll talk about today. And all of these can be mechanically exfoliated down to just a single atomic layer. We have something like black phosphorus, niobium diselenide, frankieite, which is a natural van der Waals heterostructure, natural layered material, and something like chromium bromide. And all of these, this is not an exhaustive list at all, but I chose these ones because in the screen at the moment, what you can see is a lot of different material properties. So in graphene, we can quite reductively call it the metallic or conductor. Transition metal dicalconides, the direct gap semiconductors in their monolayer form. So they have very strong light matter interactions. So here's our optical properties. Hexagonal boron nitride is the wide gap insulator. So it's a dielectric layer. Black phosphorus has some anisotropic structure. So we see anisotropic optical and electronic properties here. Niobium diselenide, although it's also a transition metal dicalconide, I mention it here because it's the superconducting material, which we can exfoliate down to 2 dimensions. And chromium bromide is the magnetic material. So we have metals, optical properties, dielectrics, superconductors, magnets, all down to 2D. So this is really a lot of materials to choose from, and many, many more that I don't put here. Okay, so we're going to talk mostly about hexagonal boron nitride today, but how does it fit into this broader range of topics? Well, in fact, before I mention that, I should mention that because it's made of boron and nitrogen, which sit either side of carbon in the periodic table, it forms isoelectronic structures to those that we see for carbon. So where we have diamond in carbon, the tetrahedral stacking, we have cubic boron nitride. And while diamond is the strongest material in existence, cubic boron nitride is the second strongest material in existence. We also have graphite for carbon, the layered structure, which we can cleave down into graphene. For boron nitride, we have hexagonal nitride, which is, again, layered structure, which we can cleave down to atomic layers. Okay, so how about hexagonal boron nitride's individual properties? Well, I've mentioned that it's already a wide gap insulator with a direct gap of about 6 electron volts, an indirect gap of about 4.5 electron volts. So it's not much use for electronic properties on its own, but it is perhaps useful for its mechanical properties because its bonding is so similar to carbon's. It shares close to carbon's strength, and it has a Young's modulus, which reduces as we move down to few atomic layers. But as we do that, we also increase the breaking stress as all these materials follow Griffith's law. So if we reduce the size of our dimensions, the breaking stress should increase. So this is a nice convergence of 2 material parameters. As we go to 2 dimensions, they become easier to stretch, but they should also be able to stretch further before they break. So this is going to be useful for our piezoelectricity. Okay, so now we can talk about boron nitride as it fits into van der Waals materials. And what a lot of research is focused on is building up van der Waals materials into so-called heterostructures. So layered structures where you have multiple layers, maybe different types, all with different properties, working complementary alongside each other. And boron nitride has principally been used as a substrate for, say, graphene electronics. And the reason why it's been utilized in this way is because when we put another van der Waals material on top of hexagonal boron nitride, we create blisters of contamination in the sample. So you can see in these atomic force microscopy images, these white marks are contamination blisters, which sounds like they should be a problem, but actually they're a result of the adhesion between, say, graphene and boron nitride, ironing out all of the contamination between the layers into these collated areas. And so all the region between these bubbles is actually atomically flat, atomically smooth, very defect-free, contamination-free area. And we can build our devices into here to get the best out of our material properties. So the best known example of this is we just then take boron nitride as a substrate, take boron nitride as an encapsulation layer for graphene, and we can get extremely high mobility electronics in the graphene layer in the middle. And this is probably one of the simplest heterostructures being produced, but it serves the purpose of explaining that boron nitride is being used as this very nice dielectric substrate for all of our van der Waals heterostructures. And all of the crystals that I showed you before, we're using hexagonal boron nitride for all of them to try and get the best out of their properties. Okay, so this is just a summary of that to say that hexagonal boron nitride is actually being used everywhere. So even when we're not interested in hexagonal boron nitride's own properties, we're still using it to get the best out of the other materials. And so this is going to be something that if we can tweak its properties slightly, or we can include some functionality, then this is going to be give us more possibilities for increasing device functionality. Okay, so let's talk a bit about our first real topic today, which is piezoelectricity. So the motivation for using boron nitride in this, I've already discussed a little bit about already, which is that when we move down to, say, monolayers to fewer layers, we can withstand more stress in our materials. So we can strain them more. And piezoelectricity is the coupling of mechanical strain with electric potential. So the more strain we can put into our sample, the larger electric potential variation we're going to be able to get with through piezoelectric coupling. Likewise, as well as being able to withstand these huge stresses, we can also strain them more easily because the Young's modulus reduces as we get to fewer layers. So I mentioned this already, but it's worth saying again that this is a really nice convergence of two effects when we go to single atomic layers. And then the final thing to say about boron nitride in this regard is that we're already building it into our devices. So anything else we can add would be really great. Okay, so where does piezoelectricity fit into two-dimensional materials? Well, it's already been demonstrated for molybdenum disulfide, the transition metal dicalgonide. And what these guys did in 2017 was they put their MOS2 on a polymer and they flexed their polymer, you can see here. And by flexing it, they introduce uniaxial strain from one end to the other. And they can use this by flexing it backwards and forwards to drive current through a series circuit. And this is quite a cool result, and it's quite a nice paper they produced. But one thing that I would like to address is that if you do it in this form, you're sort of limiting yourself to using the edges of your crystal. So here they utilize the fact that they can bend the crystal quite easily, which is using the 2 dimensions, but they're not actually using the central region of the crystal. And so we'd like to maybe try and think about how we could do that in our own experiments. Right, so let's meet our first problem, which is that hexagonal boron nitride has a centrosymmetric unit cell. And that is to say that if we invert it, we get something which looks the same. In terms of piezoelectricity, speaking specifically, that means that if I strain it, if I get a polarization in one of our layers, then because the adjacent layer is the inversion of our first layer, we'll get the same polarization in that layer, but it will be pointing in the opposite direction. So the polarization fields will exactly cancel each other out, which is why we won't see any piezoelectricity for hexagonal boron nitride. And of course, the solution, if you read the title, is to just strip the hexagonal boron nitride down to a single atomic layer. In this case, we use half the unit cell, and we no longer have a centrosymmetricity, and so we should see some piezoelectricity. So how does piezoelectricity work for hexagonal unit cells like this? Well, we need a polar bond, which we do. We have negative and positive atomic cores. Negative in our case would correspond to the nitrogen atoms, positive to the boron. And then we have to introduce some strain like this, and we'll get a polarization field associated with the fact that we've now split the charge inhomogeneously. And this polarization field will just give us a potential difference from one side to the other, given by the distance over which we have this polarization. We can also strain our sample in the other direction. And if we do this, then we get a polarization which points in the opposite direction. So we can depending on which axis we use to strain the crystal, we can change the direction of our polarization. And actually, if we begin to add in some shear strain as well, then we can get polarizations in all directions. And this is generally given by this vector potential for 2D hexagons, where Uij is the strain tensor for the system. And the vector potential is quite, can be simplified for the 2D hexagons. Right, so the polarization here is then given by the vector potential times by the piezoelectric constant for hexagonal boron nitride, crossed with the z hat, crossed with our out of plane unit vector. And now, if you remember what I said before when we were talking about molybdenum disulfide, we have a bit of a problem because this cross product limits us to polarizations which are in the plane. So if we think about putting monolayer boron nitride and trying to exploit this piezoelectricity as part of a van der Waals heterostructure, what we would like is that this affects adjacent layers. We'd like to be able to put it in and use all of the material to affect adjacent layers and to see these properties propagate in the Z direction. So we need another way in which to do this, another mechanism for affecting those layers. So the way we're going to do this is through an inhomogeneous strain distribution. So let's use a simple example and create an exaggerated strain distribution across our 4 unit cells here. Something like this. So I've stretched this one. We have large expansive strain on the left-hand side, and then quite large compressive strain on the opposite side, and no strain in the middle. And when we do this, we can put some polarization fields on for our 2 strained unit cells. And what we find is on the left-hand side, we have a polarization pointing like this, but on the right-hand side, because we've changed the direction of our strain, the direction of our strain, we also switch the polarization around. So we created quite a large gradient in polarization here. And that gradient in polarization will give us an effective induced charge in our monolayer boron nitride layer. And if this doesn't seem intuitive to you, then you can think of just about counting charge here. So if I separate the sample along a line somewhere like here, you can see on the left-hand side, we have 2 positive charge, 1 negative. So we would have, say, an effective positive charge on this side. And then over here, of course, we're going to have 1 more negative charged atom than positive. So we produce a negative induced charge over here. So this is a sort of simplistic way to think about this induced charge. It's not that we have suddenly turned hexagonal boron nitride into a conductor. The electrons aren't moving. We're simply redistributing charged atomic cores around by strain. And it requires a gradient in polarization to produce this induced charge. Okay, so we have a strain field which gives us our vector potential. The vector potential gives us a polarization, and if we have a gradient in polarization, we can produce an effective charge. And this effective charge is, well, it's a real charge. It has a Coulomb force, and a Coulomb force is a 3-dimensional acting field. So this is going to be able to act in plane and out of plane. So if we put this into a heterostructure, we should be able to see the effect of this induced charge in the adjacent layers. Okay, so let's produce some samples to try and take advantage of these properties. So what we're going to do is we're going to take monolayer hexagonal boron nitride, and we're going to put it on top of graphene. Now we're going to use graphene for 2 reasons here. The first is that we can induce these contamination bubbles, which I'd discussed before. And these contamination bubbles are epicenters for strain. So they're going to be large strain producing features in our samples, and we can try and look at that and predict how the strain will appear not only on top of the bubble, but in the surrounding area too. The second reason to use graphene is because it conducts electrons. And so if we have an induced charge in our monolayer boron nitride layer, we can expect that the electrons in graphene will see this charge and move accordingly. So these are two reasons to use graphene as our adjacent layer. So we can talk about these bubbles a little bit more. Quite a lot of work has been done on understanding them, on understanding the strain in the layers that make them, and how it's related to the adhesion between the two layers which produce them. And they actually contain a huge amount of pressure, so up to gigapascals within the actual bubble themselves. And as you'd expect with gigapascals, we get a lot of strain on the surface here, but we also get a lot of strain propagating out into our heterostructure radially. Oh. And it dissipates slowly as we, in say several hundred nanometers, as we move away from the edge of the bubble. And what we saw when we put monolayer boron nitride on graphene is this on the left. So you're looking at an atomic force microscopy image, and this is just some contamination, some incidental contamination. But around the bubble, we see this very strange, almost quadrupole-like looking structures where the contamination doesn't exist in some areas, but does in others. And this clued us on to the fact that we probably have some kind of effect here around the bubbles. Okay, so we produced samples, and they look a little bit like this. I include this just for your information, for your interest. I don't expect you to be able to see the monolayer boron nitride in the very center here, but we have a graphene flake, which is the dark region here, and there's a very hard to see monolayer boron nitride in there. Of course, being a wide-gap insulator, it doesn't have a very strong light interaction, so it's hard for us to see. But if we take the dark field image, you can maybe just about see the scattering from its edges. And we produce samples like this. And when we look in atomic force microscopy, we take a topography image, we have these small bubbles in the region like this, and we can look around them to see if there's some interesting effects. And this is where we see this incidental contamination. So Dr. Andreeva had the smart idea of maybe trying to deliberately introduce some polymer onto our sample, but using polyelectrolytes. And these PEI polymers are long polymers which tend to align along electric fields. So they can feel an electric field and they want to align upon the electric field. And so we could put them on our sample, and what we would hope is that we would see something like, you know, when you put iron filings on a magnet and they follow the magnetic field lines, something like this in our sample. So we did this, and we got these very nice, very beautiful images where you can see some kind of correlation in the direction of our polymers as they interact with the bubbles in the center of our picture. So hopefully you can see here, there's some kind of azimuthal orientation around this bubble, maybe a little bit around this one. But unfortunately, this work is it's ongoing and it was inconclusive. We weren't able to get something quite out of this. But we can hopefully you can see there that there's the indication that something is going on. So what we did next was we took our samples, monolayer boron nitride on graphene, and we did some electric force microscopy. And when we do this, we can pass an AC voltage between our current, our metallic tip and our silicon backgate. And if you have an AC voltage between the tip and the backgate, you'll get forces related to the contact potential difference between the tip and the backgate, the capacitance, how the capacitance changes in the Z direction, and the dielectric of the material in between. But thankfully, we can decouple a lot of these parameters by looking at both the first harmonic of the oscillation of our tip and the second harmonic. So the second harmonic is sensitive to the capacitance, how the capacitance changes with Z and the dielectric, whereas the first harmonic is sensitive to all three of those plus the CPD. And this is the one we're going to want to be looking at, the CPD. So we can say that if we can see something in our first harmonic, but we don't see it in the second harmonic, we can isolate it as being a force due to the contact potential difference or just the potential difference between our silicon and our tip. Okay, so we measured electric force microscopy across our bubbles. What you're looking at is a topography image in the left, and then the EFM image on the right. And this is the profile that we take across, and we show you the profiles on the very right picture here. So what we can see is that the gray curve here, the topography image, follows the shape of the bubble precisely as we would expect for atomic force microscopy. The second harmonic of our EFM signal drops to 0 almost exactly where the edge of the bubble is. So these are our 3 additional EFM signals that we weren't interested in, and they drop to 0 almost as soon as we reach the edge of the bubble. But the first harmonic, it has some variation as we go across the top of the bubble, but it's hard in this region to decouple that signal from the topography image, from the topography signal. But once we leave the bubble, we find that for several hundred nanometers, we get an EFM signal propagating into our samples. And this is our piezoelectric signal. This is due to our induced charge and the strain gradient around these bubbles. We can compare this to theoretical calculations. We can look at the shape of these bubbles and plug them into our calculations and measure the electric field energy density as a function of the radial distance from the bubble. We can look at the polarization field and the induced charge sign, and we see good correlation between what we see and what we expect to see from our theory. We look at several different bubble types, and we see always the same type, always the same behavior, where the second harmonic, the dielectric signal, drops to 0 as soon as we leave the bubble's immediate vicinity. But actually the electric signal, the first harmonic, propagates hundreds of nanometers into our stack as expected from our theory. There's the theory for a bubble of this kind of shape. So as I mentioned, this difference between the first and the second harmonic is very useful for our experiments. We're basically able to reduce or neglect these 3 effects because we know that we don't see anything for the second harmonic. So let's consider exactly what's going on in our sample for our measurement. Well, what we have is a simplistic view here is we have a metallic tip here connected to our silicon backgate. And we induce some charge due to a gradient of polarization in our monolayer boron nitride layer. So this is not just polarization, but a gradient, and this induces some charge, which we can put here. We say a positive charge here. This affects our graphene layer, which of course attracts negative charge within the graphene layer. And this creates an out of plane polarization between our silicon backgate and our tip. And this will affect the electric potential between our tip and our silicon, which we see as a different force upon our tip. So this is what's going on in our sample. And so this is our mechanism for observing the piezoelectricity here. The final point to say on this is that we looked for the same effect in bilayer boron nitride placed on top of graphene and graphene placed on top of graphene. So here's bilayer boron nitride on top of graphene here and here, and then graphene placed on top of graphene here. And we don't see any signal like this, as you would expect, since when we return to the bilayer boron nitride system, we get back to a centrosymmetric unit cell again, so we don't have any piezoelectricity. And of course, for graphene, we don't have any polar bonds at all, and electrons are allowed to move, so we shouldn't see any effect of piezoelectricity for graphene either. So this is just to confirm that our measurement is really working only for monolayer boron nitride. We don't see any signal here for these 2 other systems as expected. Okay, so this is the first conclusion of this talk, which is that monolayer boron nitride is piezoelectric. And not only is it piezoelectric, but we can actually use this piezoelectricity to affect adjacent layers. So we don't just have to consider the edges of a uniform strain in our monolayer boron nitride to change the electric potential from one edge of the crystal to the other, but we can actually create a strain gradient within the crystal, and that will affect adjacent layers. So this is a really interesting mechanism, particularly for building up van der Waals heterostructures, where we're interested in affecting layers affecting each other's properties. And I'll just say a quick thank you to the collaborators, to Professor Fumagalli and Dr. Eres, who are the experts in electric force microscopy, Professor Novoselov, the expert in 2D crystals, Professor Andreeva, the expert in the polyelectrolytes and polymers, and Professor Guinea, the expert in the calculations of strain in two-dimensional materials. Okay, so this brings me on to the second but very related topic in this talk, which is ferroelectricity in twisted boron nitride. So ferroelectricity results from a different kind of polarization, which is a spontaneous polarization in our layers. And as we're going to see, we're going to have to work a little bit hard to try and manufacture this. But when we do, we're going to get quite a pronounced effect. And this is a nice image, which hopefully will make more sense once we've been through the talk. Okay, so for ferroelectricity in twisted boron nitride, we're going to move away from monolayers, and we're going to just think about the interface between two thin boron nitride crystals. So we no longer need to have a single atomic layer, but we are going to put, we're going to take two boron nitride crystals of, say, 10 layers or more, and we're going to add them together, and we're going to see how the interface changes in this system. So for hexagonal boron nitride in its natural state, we would expect to see AA prime stacking in the interface. And what this means is that if we have a boron atom, say a blue atom here, we have nitrogen on top of it in the other layer, and vice versa. So if we have nitrogen in the bottom layer, we have boron on top of it, and essentially the hexagons sit on top of each other. This is the definition of AA prime stacking. And this is one of the 3 high symmetry stacking configurations that we can have for what's called the antiparallel configuration. So all antiparallel means is that if we have one layer, which is one orientation, then the adjacent layer will be rotated relative to that layer by 180 degrees. The definition of antiparallel. And as I mentioned, AA prime is our most energetically favorable stacking configuration. And so we just say, we define its binding energy is something around 90 MeV, but I'll just say its binding energy is 0 here because we measure the binding energy of all the other stacking configurations relative to it. And for the antiparallel configuration, we can also have BA prime and AB prime stacking configurations. And these stacking configurations have higher energies. So they have less binding energy, so they're less energetically favorable. And this can be understood in terms of just lattice binding, because if we have polar molecules here, we have positive and negative charge likes to sit near each other. So it's just a simple case of lattice binding, as well as the some van der Waals contribution too. But what happens if we move our system from antiparallel, where the adjacent layers are 0 and 180 degrees to each other, to parallel, where they're actually the same orientation? So you can see that here, where I've created AA prime stacking on the left, that's antiparallel, but here we can't have AA prime stacking anymore because we would have boron on top of boron or nitrogen on top of nitrogen. So now we've switched to the parallel view. And so we have the analogous stacking for all of our antiparallel, but in the parallel case. So we switch from AA prime to AA. So we lose the prime when we go from antiparallel to parallel. But now, rather than having boron on top of nitrogen, now we have to have nitrogen on top of nitrogen, boron on top of boron. And so the same as we had lattice binding, which made AA prime stacking favorable here, this is going to work in the opposite case for the AA system. And so the So you can see now that relative to AA prime, so the AA prime stacking, AA actually has very high energy. So it has low binding energy. This means this is very unfavorable for the parallel configuration. But whereas BA and AB prime were less favorable than the AA prime stacking, BA and AB are quite close in energy to the natural configuration for hexagonal boron nitride. So it will be interesting to see what happens when we can put our boron nitrides together in this parallel configuration. Interesting to see how the interface will restructure itself. And so we can note as well that these two stacking configurations, BA and AB, for the parallel interface have the same binding energy. And the reason for this is that they're actually the same stacking configuration, but just inverted. So if I were to put a mirror in between these two planes, then I would switch from AB to BA, or I could alternately just rotate this round and put this layer on top and this layer on bottom, and I would end up with the BA stacking configuration as well. So I can get between the two of these by just a mirror plane. But another way I can get between the two of these is actually just by a translation. So if I were to translate this unit cell here by one atomic bond length along the basal plane of the bottom interface, I would get to BA stacking. And this is going to become quite important later on. Okay, so now if we want to investigate these different stacking configurations in our samples, we have to be a little bit smart about the way that we do it. So we could put two boron nitrides on top of each other and try and see something like this. This would correspond to like AA stacking, where the hexagons sit perfectly on top of each other. And then we could try and translate it by one bond length to create AB stacking. But actually a much smarter thing to do would just be to add a small twist angle to one of the boron nitrides. And then we'll create something called a moire pattern between the two of them, or a super lattice. And hopefully you can see that there is a new, much larger periodicity in this image, which I highlight with these brown hexagons here. And within these larger super lattices, we can see each different type of stacking. So we can see in the middle here, we have AA stacking. And in each of these vertexes, we would have, say, BA stacking here and AB stacking here. So we can be a bit smart about how we approach this. And if we just have a little twist angle between our boron nitrides, we can look at the behavior of BA, AA, and AB all within the same sample. We can also be quite smart in the way we approach the parallel anti-parallel configuration. So we know that boron nitride tends to stack AA prime. And I mentioned that this really just means that when I have one layer, its adjacent layer will be rotated by 180 degrees relative to it. So if I put a boron nitride on top of a monolayer terrace in a substrate boron nitride, then on one side of the terrace, I'll have, say, the anti-parallel stacking configurations. And on the other side of the terrace, I would have the parallel stacking configurations, because the difference in the monolayer terrace is already this 180-degree twist. So we can do those two things. We can create a super lattice samples where we can probe the different stacking configurations for each configuration, but we can also put our boron nitride across a monolayer step so that we can see both parallel and anti-parallel stacking configurations all in one sample. Okay, so we produce samples like this. This is a bulk boron nitride crystal, and we're looking for a monolayer terrace in the interface here. I don't expect you to be able to see it, but just for your information, they're quite hard to find. There is actually one here, and it's down there. And maybe if I show you the dark field image, you can just about see that there's some scattering from this terrace here. So these are really hard to find, but not impossible. And yeah, that's where it is. We use a series of micro manipulation and polymer steps to lift up one boron nitride from a substrate, pull it across on our polymer, and put it down on top of the other boron nitride across the monolayer step using a transfer system, something like this. And when we do it, we end up with this. So this is our top boron nitride on top of our bottom boron nitride. This is just in case you're interested to know what these kind of things look like. But what we've done here is we found our monolayer step. We got another boron nitride. We put it on top of the monolayer step in the bottom boron nitride. And now we're going to do some electric force microscopy. I described the operation of this before when we were looking at piezoelectricity. And let's see what we can see. Okay, so we see something like this. So this is, on the left, you're looking at just AFM topography image of our flake. This is the edge of our top boron nitride. And running through the middle here is our single atomic terrace in our bottom boron nitride. And on the right-hand side, you can see our EFM signal. And what you can see is that we have this very regular periodicity in EFM signal, which doesn't exist in topography, and it cuts off exactly where the monolayer step is. So this is a really good indication that we have anti-parallel or parallel on one side of this monolayer step, whereas parallel or anti-parallel on the other. So we have the inversion across the monolayer step, and we're seeing something really interesting for one of these configurations. And so when we produce lots of samples like this, we see a lot more of these hexagonal-like domains. And they have different sizes, different, which really just relates to the exact alignment between the hexagonal boron nitride crystals. But you know, if you look here, we've got 2 microns. So we're getting triangular domains, triangular superlattice with 2 micron-sized domains. So this is really quite nice images. One thing I like about this image is that you can see exactly where the top boron nitride ends, and that we see that the EFM signal becomes perfectly uniform when we move off of the top boron nitride. And so this tells us that this signal is exactly related to the interface between our 2 boron nitride crystals, and not some other feature within the boron nitride that we would need to understand. So we can look at another system where we see similar triangles to try and understand our own system. And this is the twisted bilayer graphene system. This is an STM image of 2 graphene layers placed on top of each other. And this is useful for us because not only does it look very similar to our system, but actually for bilayer graphene, we can't have the anti-parallel configuration. Because graphene has 2 identical sublattices, we can only ever have the parallel configuration. So we know that we produce these triangles when the interface between the 2 crystals tries to reorganize, tries to create a system where it has preferential stacking in as much of the interface as possible. The only problem it has is that the BA and AB stacking configurations for a parallel interface have exactly the same energy. So when they compete over which takes up more of the interface's area, because they have exactly the same energy, they end up taking up exactly the same amount of the area. And so that's why we see these triangular domains. So one of them is AB and one of them is BA. And hopefully you can see that this compares really nicely with our work on twisted hexagonal boron nitride interfaces. So this suggests to us that our hexagons are probably for the parallel case, and they're probably, we're seeing the difference between BA and AB. And so we can return to our little schematic here. So we have a superlattice where we see AA, BA, and AB. And if we overlap what our triangles would be, essentially our triangles would look like the BA and AB configurations, and the AA stacking, which remember for parallel is very unenergetically favorable. This becomes a small area of our superlattice area, and the BA and AB take up larger areas, and in fact equivalent areas to each other because they're they have the same energy. Okay, so this is just a summary of the energies we saw before. So for AA, very unfavorable, very high energy stacking configuration, whereas AB and BA have the same energy. So we can do some theoretical calculations to relax this system and find out how the interface will organize itself. And what we find is that for the parallel configuration, we find exactly what I've just described, that AB and BA configurations share the same amount of the unit cell, and that the AA stacking configuration is compressed into these small areas because the interface really doesn't want to have any AA stacking at all, because it's energetically unfavorable. This contrasts to the anti-parallel case, where AA prime is the most energetically favorable, and we would expect to see hexagonal unit cells to our superstructure, where both BA and AB are less energetically favorable than AA prime. So this guy really can just maximize its area of the interface. Okay, so now we understand why we're seeing triangular domains, AB versus BA. Now we need to understand why we see them at all. What is the contrast that we're observing in our EFM signal? Because we don't see anything in topography, but we do see it in electric force. So what we do for this is we measure the force on our tip as a function of the DC voltage between our silicon and the tip itself. So we're measuring the electric field through our sample, and we change the DC voltage. And of course, this will depend on the work function difference between the tip and the silicon. But ultimately, we can make the force minimum when the potential difference between the tip and the silicon is 0. So when the potential difference is 0, we get the force at a minimum. And what we find is when we look at one domain, say the bright domain here, 1, versus the dark domain here, 2, there, the DC voltage we have to put in to get to this 0 force point is different. And when we measure this DC voltage difference between the two domains, we find that it's perfectly uniform when we look at different domain sizes. So we go from the limit of our resolution, which is something like 10 nanometers, all the way up to micron domains, and it's always the same difference in voltage between the two domains. And this tells us that this is not a piezoelectric effect like we saw in the first half, but this is actually a stacking effect to do with the AB and BA stacking themselves. And the magnitude of this voltage corresponds to a polarization across the interface of about 6 millicoulombs per meter squared. So this is when I have to give a little bit of bad news. During the pandemic, we were actually scooped on the ferroelectricity part of this. So I have to mention that these other guys were able to do this nice experiment where they looked at single AB or stroke BA domains, and they were able to, using an electric field, change the direction of this polarization. So what they're doing here is they're just measuring the main Dirac point in graphene, which they place adjacent to their twisted bilayer. And when they put a strong enough electric field, they can actually shift the main Dirac point. And this corresponds to reversing the sign of our polarization in our AB or BA domains, so switching from AB to BA. We can understand this simply by looking at what I said before. So if we have AB, where we have boron on top of nitrogen, and then the nitrogen over the vacancy in the lower layer, all I have to do is translate this up by 1 atomic bond length, and I get to the BA system. So we just can go backwards and forwards between these, and all it requires is a small translation between two equally energetically favorable stacking configurations, and we can switch the polarization. So this is what we can observe, and this is how we get to ferroelectricity across our domains. Okay, so how long have I got left? Only a few minutes. Okay, so now that we know that our polarization, our spontaneous polarization out of plane is a result of the AB and BA stacking, we can switch between the two of them by putting an electric field across the interface, it's useful now to think about, well, why are we getting a polarization here? And we can do this by analogy or by looking at the other Group III-nitride crystals. And these are quite famous for having large spontaneous polarizations, particularly in their wurtzite form. So this is scandium nitride, which is expected in its hexagonal form. So you're looking through the planes here. So this would be the hexagonal form. You're looking at each layer. This would have 0 polarization. And when we start to displace the nitrogen atoms up between the layers, we start to introduce a polarization. So we have hexagonal form, and then the wurtzite form, which is where the displacement is 0.25 of the unit cell distance. And then the rock salt, where it's 0.5, has the biggest polarization, where we've displaced the nitrogen atom up by half of the interlayer distance. And so essentially our polarization is coming from just displacing one of the atomic positions out of plane relative to the other one. So we can consider how much we would have to displace our nitrogen atoms to create our polarization in our case. So if we take the hexagonal phase, we can start to think about how much we would have to move these up to produce an out-of-plane polarization for our system. And this is given, we can have quite a simple model for this, where the polarization is just equal to 1 over the unit cell volume times the sum of like the weighted charge against the position within the unit cell. So we can simplify that further to this equation, and we can get that the distance delta that we would have to move up the nitrogen atoms or move down the boron atoms, whichever way you like to think about it, is just our polarization in the z direction times the volume of our unit cell over the magnitude of the charge difference between boron and nitrogen. So this is just the polar nature of our bond. If it's 0, of course, we'd have to displace them an infinitely large distance. And when we put our numbers in, we get a displacement of about 4.7 picometers, which compares to our interlayer distance of 330 picometers, so about 1.5%. So let's say one of our atoms is just shifted up by 1.5% of our interlayer distance, and this is what's producing in the interface layer our polarization. The analysis there is a little bit too simplistic because we've assumed that just the atoms are the only contribution to polarization. Actually, we need to include some the electronic wave function contribution as well, the shifting of the electronic wave functions. But this is a little bit more complicated, and so it's easier just to stick to this to kind of give us an order of magnitude estimate. And the last thing to do, I don't want to overrun on my time, so is just to compare. So we looked at the wurtzite form of scandium nitride, and we can compare to the other common Group III-nitrides, which have polarizations in their wurtzite form, and compare the magnitude of our polarization to theirs. And so if we look at aluminium nitride, gallium nitride, and indium nitride, we're actually not doing too badly, because this is within, let's say, within an order of, or let's say an order of magnitude off from the average of these three, which isn't too bad because these are actually wurtzite. Right, so this is a structural change which produces this displacement of atoms out of the plane. Wurtzite is a sort of tetrahedral form of stacking, whereas planar hexagonal is, of course, planar. So we wouldn't expect to have a polarization which would even be comparable to these. But we can understand why it's actually quite a big polarization in our case by just thinking about the bonding, because this is sp2 bonding, whereas over here we should have sp3 bonding, which actually reduces the, increases the likelihood of the electrons being found on the non-nitride atom, whereas here we would have quite a large polar nature between our boron and nitrogen. So this is actually quite a large polarization for what we would expect even though in absolute terms it's smaller than these others. Okay, so the final thing to do on this topic is just to say thank you to all the collaborators, again to Professor Fumagalli and Dr. Erez for their expertise in scanning probe and scanning electric force microscopy, to Professors Novoselov and Galin for their expertise on 2D materials, and then to Professors Guinea and Wallet for their in-depth calculations as to the relaxation at the interface. And then the last thing to do is to say thank you to you for listening, and to invite any questions if there are any.
Okay. Now it's open to the question. Is it? Let's see. Any question? Maybe you initializing the question.
Yeah, sure. So Colin, thanks a lot for a very nice talk. So I like this talk very much for two reasons. So first, on your piezoelectric part, so it's based on bubbles, right? And I think it shows a very nice shift that we have had in the scientific thinking in 2D materials. So if we go back to like early days of heterostructures devices, people were fighting with these bubbles to get very nice clean interfaces. And then gradually people started thinking that there is nice, interesting physics in that. So as you mentioned, there are huge, there's huge pressure inside that you can use to induce pressure to some polymers that you trap inside. So we know, for instance, from optical experiments that if you look at the cross section of such a bubble and how the band gap changes, you actually, for TMDC, for instance, boron nitride, you would have a minimum at the top of the bubble. And that means that if you create charges, for instance, photoelectric through photoexcitation, you will get a kind of funneling effects, putting electrons at very high density at the top of these bubbles, and even more complicated kind of traps around the perimeter of the bubble. So I wanted to ask you, so what motivated you to look at the bubbles? Was it just coincidental, or was there like thought, it was prediction first that there would be interesting effects there?
So the motivation is twofold, really. One is coincidence, and one is that, as you say, these are kind of nice systems to look at. So I just returned to this image here. This image is actually maybe the first indication we had that piezoelectricity here would be a nice thing to look at. So this is an incidental thing. So we saw this contamination form all around this bubble in one of our monolayer boron nitride samples. And the effect is so strange, and I can't really do justice to the fact that when you look across this sample, you see this for all of the bubbles. You can see for this big bubble here that we have something related to the bubble in contamination, but you can also see here there's a little bubble where we also see the same thing coming out from the edge of the bubble. And this gave us an indication that maybe there's something quite a strong effect here. And this got us thinking that, well, these materials can withstand huge strains. It's expected to be piezoelectric in its monolayer form. Maybe these bubbles, which, as you say, are epicenters for these huge or relatively large forces, maybe they're actually producing a large effect. So this was kind of the serendipitous moment for this project. But the second reason that motivated us to use these bubbles is that maybe it's a little bit earlier, yeah. So if we go to this picture here, so the bubbles iron out these very clean regions. And so one of the problems with our electric force microscopy measurements might be that if you tried to measure, say, the effect of piezoelectricity on top of the bubble, you would have to decouple a lot of different signals. So you have topography changes across here. You also have unknown materials and distributions within this bubble. But what we know from the bubbles is that they have this strain distribution around the edge. And here, there's no topography here at all, really. This is where we get these atomically smooth areas. And so it's a system where we've already decoupled the topography from the strain. So you might also consider trying to introduce strain, using nanopillars or other techniques like that. But they have the same problem where actually you would need to decouple some nanopillar topography signal from your electric force microscopy signal. But the bubbles we knew were an inbuilt system where we already had this kind of decoupling. So those are the two things. One is the sort of coincidence that we make some samples and we see some nice features or some interesting features in contamination. But the other side of it is this, we know that this system produces a nice clean area for us to look at. I hope that answers your question.
Yeah, thanks, Colin. So the second thing that I was wondering, so we see more and more physics done with a twisted layer, and that is a unique property of 2D materials. So we've seen, for instance, superconductivity in twisted graphene. We've seen hybridization of states and appearance of new excitonic states in transition metal decalcogenide. So now we have another example that you show, which is ferroelectricity in boron nitride. So the main difference between these different techniques is the scale, right? Because if you do it in transport, you pretty much probe this moire macroscopically. And you do it in optics, you have a resolution of, let's say, about a micron. But here you image this moire pattern quite nicely. And as you can see, and you probably can expect, it's not perfect, right? If you make a perfect twist, you would have a perfect periodicity. And here you see that this pattern is a bit inhomogeneous. So from your, and that's obviously gonna come from imperfections of the topography pretty much. So can you kind of say, like, how many units from your experiments can you say you have like a very, very homogeneous pattern? And at what length scale does it become inhomogeneous? And then maybe what is like the main features that are introducing this inhomogeneities into the moire pattern?
Right, good question. So we deliberately made our samples. So the sample that you're looking at on the left-hand side here is 4 layers of boron nitride on top of a thick boron nitride. So the inhomogeneity here comes from the fact that the 4-layer boron nitride has some macroscopic strain distribution in it. So so here, where we have a large periodicity, we know that the alignment between the two crystals is very good. And then we have a crease in the 4-layer, and that's what produces this discrete change from here to here. So we have a crease, the angle between the two crystals changes discretely, and that produces the discrete change in periodicity. But we also see some elongated superlattice here, and it changes as a function here. Well, these layers can, because they, as you move them down to very, very thin, they become easier to include strain in them. It includes some macroscopic strain, which doesn't have a discrete creasing point or folding point or something like that. So this should actually be fairly straightforward to tweak, because if we go from, say, 4 layers up to 10 layers, then the ability to strain 10 layers is about 2.5 times harder than it is for 4 layers. So 10 over 4 is just 2.5. So it's about 2.5 times the Young's modulus. And so these macroscopic strains are much harder to incorporate into an interface between a 10-layer crystal and another boron nitride crystal. So we might consider that as one way to produce a more uniform superlattice. And certainly we do see some regions of uniform. I don't think I include too much on it here, but okay, maybe we see some fairly uniform regions in this sample. But for this, we were looking really just at understanding what we're looking at and what it is. But I think it is possible to tweak this situation by just changing the number of layers and maybe how precisely you put them down, or how many layers on each side. You can tweak the macroscopic strain within the layers. Right? Does that make sense?
Yeah. Perfect. Thanks a lot. I think we have some questions for the audience, so maybe we can move to these now. Jingsheng, do you want to read them, or should I read them?
Yeah, the first one, I think, okay, Colin, you can read maybe, yeah.
Okay, yeah, I just see now. So So the question is single layer graphene on monolayer boron nitride, I'll assume, because if I put single layer graphene on, like, say, bulk hexagonal boron nitride, of course, because bulk isn't expected to have piezoelectricity, we wouldn't expect to see some piezoelectricity there. So I'll assume the question is single layer graphene on monolayer boron nitride. And do we expect to see piezoelectricity there? I think the answer, oh, I can't get rid of this. How do I can move it to one side maybe. Okay, so I think the answer to that question is really, let's go back to the theoretical look at what is in these bubbles. So we have to go quite a long way back. Okay, here. And so what we can say is that just due to the fabrication process, something like this will happen. So we would expect that if we have just a monolayer boron nitride as our substrate, and then we put graphene on top, we would expect that the bubble would more affect the layer you put down second, because your monolayer boron nitride is going to be on a substrate, silicon dioxide or something like that. So its ability to bend downwards is going to be limited by the fact that it's already on a substrate. It's an interesting question though, because boron nitride has a slightly weaker Young's modulus, you might expect to see something in the region around, because as both layers will try to relax the strain. So you might see something, but I would certainly expect it to be a more pronounced effect when the monolayer is on top, when it is the second one to be deposited, because then it's the emphasis is on the monolayer boron nitride to accommodate more of the strain. So I hope that answers the question. So in short, you might see something, but I would expect that if you put the monolayer boron nitride onto a substrate of graphene, that's where the effect will be more strongly observed. Okay, a few questions in slide 17. Okay, let's go back to MOS2. So in this result, so the question is about MOS2, and when we bend the polymer substrate, what's the sort of role of rippling stroke curvature on the result here? Well, the bending here, the curvature is the introduction of positive expansive strain. So that's what's introducing the strain here. And so because we have a piezoelectric material, that strain, when you increase the curvature, that's what causes our potential difference from one side to the other, and they use that to drive the electrons in a circuit. You can think of this curvature as being like, so what's the shortest distance between 2 points? What's the shortest distance between my two contacts? Well, if I leave my polymer flat, then I have a straight line. So this is the shortest distance. But then if I bend my substrate and I have that same distance, but I now have to follow a curvature around, then this distance across the polymer layer will be bigger. And this causes the strain, because the crystal has to follow this much longer path. So this causes the strain in the crystal. With regards to rippling, I think rippling is a feature of compressive strain. So what do you mean rippling in terms of the polymer? I think rippling in terms of the polymer would probably not have an effect on their result, but I'm not sure. And rippling within the MOS2 would be a feature of the compressive strain, but they're not actually creating compressive strain in their samples. How can inhomogeneous strain be precisely controlled for potential applications? That's a tough question to answer. So it's become a very hot topic actually in two-dimensional crystals right now, is how do we engineer strain into samples? In answering that, it would be probably its own talk. I've spoken about a few things, like we use just the bubbles, which are kind of an incidental part of our samples, but people can use polymers and stretch the substrate, like in MOS2. People also fabricate nanostructures and then place their 2D material on top of the nanostructures. And this creates large strains when the crystal is required to conform to a non-flat substrate. But to be honest, the answer to the question about creating inhomogeneous strain is a really big one. It's a really good question, and it would take quite a while to give a comprehensive answer, but there's lots of different ways to do so. The final question here is, how do you think density functional theory calculations and other simulations can support your experimental results? Well, we have, so essentially we're thinking about how the electrons behave. So I gave in the ferroelectricity section, sorry, I have to jump forward quite a long way. I gave some very simple analysis at the end about how we can consider our ferroelectric polarization to be just the displacement of atoms. So if we look here, I just said, okay, this has a set positive charge and this has a set negative charge. And if I displace one of them relative to the plane, then I will have a net out of plane polarization. And I then mentioned that actually this simplistic view misses off electronic wave functions. So we would have, so if we can include this in our calculations, we get a better idea of how much we're deforming this, where this deflection is coming from. Because you could actually imagine that we could have this effect completely dominated by electronic wave functions. So the atoms just sit in plane as they are, but the electronic wave functions are the things which shift due to the van der Waals interaction with the layer below, and that could be the opposite of what I described, where the electronic wave functions are dominating over the atomic movements. In reality, they're both probably present, and something which is so how could understanding that help our experiments? Well, you might think about the other 3 nitride systems, because what they do is they include different alloy amounts of, say, gallium or aluminium or indium, and they can change this distance. If I go back here, they can change this delta parameter by just changing the amount of, say, gallium they use compared to aluminium or something like this. And they get different polarizations, of course, depending on the different displacements here. So it would be interesting to know is what effect do we have from atoms moving? What effect do we have from wave functions moving? Because then if we try and change this system further, we might have an idea of how much we're going to be able to change it by changing the composition. So I hope that answers your question. Okay. Does the polymer contamination affect the formation of the superlattice structure and EFM measurements? Okay, that's a good question. So does polymer contamination affect our measurements? Let's minimize that. So actually something that I didn't mention while we were doing this talk was that polymer contamination is actually deliberately not a feature of our piezoelectricity measurements. One of the reasons why we, let's keep going back. So we had this contamination here, but this is incidental. I don't know whether this sample was just left or maybe just treated in a particular way, but we ended up with contamination. We see this, but all the samples we make from then on, we're thinking about how can we decouple our EFM measurement from any topography signals. And so this is why actually we don't contact the graphene itself, but we contact the silicon, because then we don't have to do any fabrication techniques. We don't have to use it, we don't have to use any more polymers on the surface. We don't have to use any wet chemistry or anything like that to create contacts to graphene. So we're deliberately creating systems for this case where we have nothing here, no contamination. So we're making the sample as quickly as possible. We contact the silicon, so we don't have to do any more fabrication on the surface, and then we measure it within a day of making it, so that the polymer contamination is kept to a 0. So actually, all of this signal we can say is really not related to topography or not related to contamination at all. The second half of your question, so how does it affect superlattice formation? Then I have to jump forward again. So let's see, so we can actually see some contamination in the images here. So here we have a large piece of some contamination. Do we see some bubbles here? No, we don't, but we have contamination on the surface. We have contamination, maybe something here. I'm not sure exactly what this is, but contamination in this case doesn't affect our overall measurement because the effect is so strong that we're not worried too much about contamination. If there is any contamination between the layers here, we can expect that it would be ironed out into these big bubbles that we see in the first half of the talk. I'm actually a bit surprised that I don't have one to show you. It would be interesting to show you because, you know, these bubbles have a strain distribution around them. So we would see that strain distribution in the superlattice as well, but I'm disappointed to say that I don't have something like that to show you. But in short, the contamination is not a problem for looking at this effect because of this self-cleaning mechanism, because of this ironing out of the interface. I hope that answers your question. Okay, thanks for the talk. So how do we introduce the twist between boron nitride with such control? So that's a fabrication technique. It's a good question. So let's go back and look at our sample. So I showed you this picture because I think it's interesting for people to know that these monolayer terraces and stuff, they are possible to see, but they're very difficult. But if we look at this image on the left, this is like a monolayer, sorry, not monolayer, this is just a boron nitride flake. And what we can see is that it has some very straight edges. So at the top here, so these edges are very straight, almost suspiciously straight. And actually this is because these materials, when you mechanically exfoliate them, they tend to crack along the zigzag and armchair directions. And it's the same is true for pretty much all van der Waals 2D crystals. And so what you can do is you have these straight edges. You can then take a straight edge in this crystal and then take a straight edge in the crystal that you put on top. So you have two hexagonal boron nitrides, you bring them together, but they both have this very straight edge, and you align these straight edges together. And because you know that they will be zigzag or armchair directions, we know that we'll have almost perfect crystallographic orientation. In terms of getting precise alignment, i.e. the difference between 0.1 degree, 0.2 degrees, it's a bit of a random process. I'm afraid our mechanical transfer stage, something like this, it has a rotation, but we're really only getting alignment which is plus or minus at best half a degree or something like that. And we're just hoping that we see, hoping that we get it right. Maybe it has a slightly better angular resolution than that, but it's not, we can't do it perfectly. So we can only get, say, plus or minus 0.5 degrees in our samples. Okay, does that answer the question? Yeah, I hope that answers your question, Aravind. And okay, and that's not a question. Okay, are there any more questions which people would like to ask?
I have one question, Colin. Yeah.
Sure.
So for, you use a PFM to measure the ferroelectric property, right?
Yes.
Okay, for PFM, normally they measure the charge. So, this one exposed to a lot of the environments, maybe at the surface, they're screening some, charge. So how this electrostatic effect, affect the signal of the PFM?
Do you mean the piezoelectric stuff?
Yes.
Yeah. Okay.
Yeah, that's, I know even some really materials, even the for the zinc oxide, some other materials all measures very good. Piezo phase slope, even the phase change, phase contrast, right? Yeah, just due to the some charge injection, also the surface electrostatic effects. Okay, how do we exclude this one to get to confirm that is really ferroelectric property?
So in our case, what we do here is we use so we're comparing the first and second harmonic. So I kind of simplified and I sort of went quite quickly over the EFM measurements. But what we're doing is we're passing an AC voltage to our tip, between our tip and our silicon. And the force on the tip and the silicon is we're going to measure how much of an effect it has on the tip's vibration in the first harmonic and the second harmonic. And so the second harmonic has a force proportional to a function of a lot of different effects, essentially capacitance and things like this. This first harmonic, however, has all of the same features, but it also has the contact potential difference. So what we can do is we can say, well, if we see something in the first harmonic and not the second harmonic, we know that this is due to the potential difference from the tip to the silicon. And so this allows us to take out, say, capacitance and dielectric changes. And so when we look at our profiles, what we can see, the red curve here, this is the second harmonic, and it drops to 0 just as the topography drops to 0. But the first harmonic stretches hundreds of nanometers into the stack, so way beyond our resolution, our measurement resolution. And so we can say that this is due to the potential difference. Now, how do we exclude the idea of, say, contamination or things like that? Well, in that case, we just have to look at the topography signal and say that we don't have any serious contamination. And we can look at the map of EFM to say, well, this is something which follows the shape of the bubble. So topography, you can see here, the black curve is really, once we leave the bubble, has 0 roughness. And also, when we look at the map of the EFM signal, if we had, say, like some charge trap or some local charging or something like this, we would not expect it to so precisely follow the edge of the bubbles. Does that answer your question?
Yes, thank you. Yeah. Thank you very much. Very nice talk. Okay, any more question? If no more question, okay, thanks. Okay, Dr. Woos give us this wonderful talk. Okay, thank you.
Okay, thank you very much. There's one last question. Zong Han, can AFM measure superlattice? So I assume that means, can we see the ferroelectric, the twisted boron nitride superlattice? Can we see it in AFM topography image? The answer is no, we can't.
Okay. Bye-bye.
Okay, bye.